Introduction.
Prateek, you know what? Today our math teacher taught us about relations and functions.
Relations. But this is an English topic.
Yes, the concept of the term relation in mathematics has been drawn from the meaning of relation in English language.
Oh, that is interesting.
According to the term relation, the two objects or quantities are related if there is a recognizable connection or link between the two objects or quantities.
I know that. Tell me more about it.
Okay, come with me. I will tell you.
Objectives. At the end of this lesson, you will be able to define different types of relations, explain types of functions, learn composition of functions and invertible function, explain binary operations. Types of relations 1. We know that a relation in a set A is a subset of A cross A. Different types of relations are empty relation, universal relation, reflexive relation, symmetric relation, transitive relation, and equivalence relation. Let us go through them one by one. Empty relation. A relation R in a set A is called empty relation if no element of A is related to any element of A. That is, relation R is equal to null set, which is a subset of A cross A. Universal relation. A relation R in a set A is called universal relation if each element of A is related to every element of A, that is, R is equal to A cross A. Types of relation 2. Reflexive relation. A relation R on a set A is called reflexive if x belongs to in R for all x belongs to in A. That is, R is reflexive on the set A if x is related to x under the relation R for all x belongs to in A. Symmetric relation. A relation R defined on the set A is called symmetric relation if x, y belongs to in R, implies that y, x belongs to in R. Transitive relation. A relation R on a set A is said to be transitive if A1, A2 belongs to R and A2, A3 belongs to R, implies that A1, A3 belongs to R for all A1, A2, A3 belongs to A. Equivalence relation. A relation R defined on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. Example. Check whether the relation R defined in the set 1, 2, 3, 4, 5, 6 as R is equal to A, B such that B is equal to A plus 1 is reflexive, symmetric, or transitive. Answer. Let A is equal to 1, 2, 3, 4, 5, 6. A relation R is defined on the set A as R is equal to A, B such that B is equal to A plus 1. Therefore, R is equal to 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. We can find A, A does not belong to R where A belongs to A. For instance, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 does not belong to R. Therefore, R is not reflexive. It can be observed that 1, 2 belongs to R, but 2, 1 does not belong to R. Therefore, R is not symmetric. But 1, 3 does not belong to R. Therefore, R is not transitive. Hence, R is neither reflexive nor symmetric nor transitive. Types of functions. According to the nature shown by a function, it can be classified into different types. 1-1 or injective, onto or surjective. 1-to-1 function. A function is said to be 1-to-1 function if every element of domain of the function have its own and unique element in range of the function. A function from set A to set B is said to be a 1-to-1 function if no two or more elements of set A have same elements mapped or imaged in set B, or no two or more elements processed through the function give same output. Onto function. A function is said to be onto function if two or more elements in its domain have same elements in its range. Or a function from set A to set B is said to be onto function if two or more elements in set A processed through the function produces same output or same element in set B. A function f from x to y is both 1-1 and onto, then it is said to be 1-1 and onto or bijective. Example. Check the injectivity and surjectivity of the function f from n to n given by f of x is equal to x square. Answer. Function f from n to n given by f of x is equal to x square. It is seen that for xy belongs to n, f of x is equal to f of y, which implies that x square is equal to y square, which implies that x is equal to y. Therefore, f is injective. Now 2 belongs to n. But there does not exist any x in n such that f of x is equal to x square is equal to 2. Therefore, f is not surjective. Hence, function f is injective but not surjective. Composition of functions. It is possible to combine two functions by adding, subtracting, multiplying, or dividing two given functions. There is another way to combine two functions to create a new function. It is called composition of two functions. The term composition of functions or composite function refers to the combining of functions in a manner where the output from one function becomes the input for the next function. Let function f from a to b and function g from b to c be two functions. Then the composition of f and g is denoted by g of f is defined as the function g of f from a to c given by g of f of x is equal to g of fx for each x belongs to a. Example. Let f, g and h be functions from R to R. Show that f plus g of h is equal to f of h plus g of h. Answer. To prove f plus g of h is equal to f of h plus g of h, consider f plus g of h x, which is equal to f plus g of h of x. On solving we get f plus g of h is equal to f of h plus g of h. Hence proved. Invertible functions. A function f from x to y is defined to be invertible if there exists a function g from y to x such that g of f is equal to ix and f of g is equal to iy. The function g is called the inverse of f and is denoted as given. Thus, if f is invertible, then f must be 1, 1 and onto. Conversely, if f is 1, 1 and onto, then f must be invertible. Theorems. If function f from x to y, function g from y to z, and function h from z to s are functions, then h of g of f is equal to h of g of f. Let function f from x to y and function g from y to z be two invertible functions. Then g of f is also invertible with inverse of g of f is equal to f inverse of g inverse. Example. Consider function f from R to R given by f of x is equal to 4x plus 3. Show that f is invertible. Answer. Function f from R to R is given by f of x is equal to 4x plus 3. 1, 1. Let f of x is equal to f of y, which implies that 4x plus 3 is equal to 4y plus 3. It implies that 4x is equal to 4y. It implies that x is equal to y. Therefore, f is a 1, 1 function onto. For y belongs to R, let y is equal to 4x plus 3. It implies that x is equal to y minus 3 upon 4, which belongs to R. Therefore, for any y belongs to R, there exists x is equal to y minus 3 upon 4, which belongs to R, such that f of x is equal to f of y minus 3 upon 4 is equal to 4 into y minus 3 upon 4 plus 3, which is equal to y. Therefore, f is onto. Thus, f is 1, 1 and onto, and therefore f inverse exists. Binary operations. A binary operation is simply a rule for combining two objects of a given type to obtain another object of that type. We first learned of binary operations in elementary school. The objects we were using were numbers, and the binary operations we investigated were addition, subtraction, multiplication, and division. In this lesson, binary operations need not be applied only to numbers. Definition. A binary operation star on a set A is a function star from A cross A to A. We denote star A comma B by A star B. Did you know? Every object in this universe revolves around the fact of relation and functions. Every concept of math has emerged from the theory of relation and functions. The concept of function has evolved over a long period of time, starting from R. Descartes, 1596 to 1650, who used the word function in his manuscript Geometry in 1637 to mean some positive integral power x to the power n of a variable x, while studying geometrical curves like hyperbola, parabola, and ellipse. Summary. Let us summarize what we have learned. Empty relation is the relation R in X given by relation R is equal to null set, which is a subset of X cross X. Universal relation is the relation R in X given by relation R is equal to X cross X. Reflexive relation R in X is a relation with a comma A belongs to R for each A belongs to X. Symmetric relation R in X is a relation satisfying A, B belongs to R implies B, A belongs to R. Transitive relation R in X is a relation satisfying A, B belongs to R and B, C belongs to R implies that A, C belongs to R. Equivalence relation R in X is a relation which is reflexive, symmetric and transitive. Equivalence class A containing A belongs to X for an equivalence relation R in X is the subset of X containing all elements B related to A. A function f from x to y is 1, 1 or injective if f of x1 is equal to f of x2, which implies that x1 is equal to x2 for each x1, x2 belongs to x. A function f from x to y is said to be onto function if each element of y is the image of some element of x, that is, for every y belongs to y, there exists some x belongs to x such that y is equal to f of x. A function f from x to y is 1, 1 and onto or bijective if f is both 1, 1 and onto. The composition of functions f from a to b and g from b to c is the function g of f from a to c given by g of f of x is equal to g of fx for each x belongs to a. For function f from a to b, if there exists a function g from b to a such that g of f is equal to ia and f of g is equal to ib, where ia and ib are identity functions, then f is called an invertible function. A function f from x to y is invertible if and only if f is 1, 1 and onto. Given a finite set x, a function f from x to x is 1, 1 respectively onto if and only if f is onto respectively 1, 1. This is the characteristic property of a finite set. This is not true for infinite set. A binary operation star on a set A is a function star from A cross A to A.